Okay, so now I'm going to talk about how it is applied to JPEG images. And JPEG images are a bit more confusing. As you can see here, we've got 6 stages. The first stage is to break an image up into 8x8 blocks. And if you look closely, you might be able to see the vague 8x8 blocks on the screen. And these are 8x8 blocks of individual pixels. What we then do to these 8x8 blocks is we apply something called the DCT. And what this does is it basically represents that 8x8 block of pixels as a series of different frequency cosine waves. And generally, generally we can do this to luminance, because luminance is the brightness of an image, and it can generally be compressed to a much greater extent than chrominance, chrominance is the variation in color, and it will have less impact, so it'll be less visible to anyone looking at the picture when we compress luminance in the DCT. So an example of how this might work is if we take this 8x8 block of pixels, and in this 8x8 block of pixels there's no variation in brightness. As you can see here, there's no difference between any of the pixels, so what we're going to do is the only wave that will represent this is the wave in the top left, because the wave in the top left is the wave which represents no change, and each of these frequency blocks, if you like, these will come up a certain amount of times depending on what the grid of pixels is like. So looking at this one, we've got a gradient going from the top to the bottom to the top, of dark to bright even. And if we look at the grids, we're just going to choose maybe 2 or 1 for this one, because the left side, the second top one, represents dark going to light, and so that might be the one we choose here. But when we get to more complex ones, like this one, which is the gradient of top left to bottom right, we're going to have to combine many different waves. And generally, it's going to use a lot of different waves, because it's not generally just going to be one gradient, it's going to be a mishmash. So looking at an example of this, we've got this 8x8 grid of pixels here, and we've got actually the DCT coefficients of each of these pixels here. And what this says is the coefficients are how much of each wave appears, so it's kind of like the weighting. So if a wave appears a lot, we're going to weight it highly. So in this image, since it's quite bland, there's not much change in, the bottom right whole side of the image has got very little change. There's going to be a lot of this element, which is the top left one. And in this image, there's almost none of the bottom right, well, there is none of the bottom right ones. All these 4 appear absolutely not at all in this, because it's not really like a checkerboard if you look at it. What we then do is we quantize this block of DCT coefficients. And what we're going to do is we're going to divide the elements by the quantization table elements. And for high compression, we're going to divide it by bigger numbers, which will make it all smaller. For lower compression, we're going to divide by smaller numbers, which is going to keep them, well, it's going to keep them bigger than they would be if they were high compression. We then take this quantized block of things and we're going to scan it in using zigzag scanning. So what this does is it's just like you see in the diagram here. We're going to take the top left element, and then the one to the right, and then the one below the top left, and we're just going to continue along entering in all these values in a zigzag motion. And this is where we might insert a method. So we might insert things into the quantization table, so into these DCT things that have been changed. So if we want to hide this byte here, which is 0, 110, 100, what we're going to do is we're going to hide them, each of these, in the end of one of the values. So the first value is 26, and we're looking to hide the bit of 0 here. And the binary of 0, the conversion is 11010. So we're not going to need to change anything, because the last digit is already what we need it to be. We then look at the second one, which is 3. We need the end of 3 to be 1, and it is, because 3 is an odd number, so it's going to be something to the power 2 add 1. And we'll continue along 8 times. So we're going to continue along 3, and then to 0, and then to 3, and then to 3, and then to 6, and we're just going to keep going. And in an 8x8 block of pixels, if you do the maths, since we're hiding something in the end of every single one, we could store 8 different letters. But generally we won't do this, and we won't want to change these zeros. It's just a hypothetical, because these zeros, if we were to add lots of different patterns, it would start to make a big difference. And especially if we were conducting statistical attacks to see if steganography was here, these are almost always 0, and if they were able to see that lots of these weren't 0, they'd almost always certainly be able to tell that something had been done to this image to hide something, because it's very unusual for these ones to be 1s. The final stage is Huffman coding, And this really, it's not involved in steganography, but what it does is it compresses down the zeros at the end. It's going to save lots of the space, and it's going to make it take up less space. Thank you for listening. I hope that's made it a bit clearer, and yeah, that's all.